Thank you for joining my presentation. My name is Zhang from the National University of Singapore. Here I'd like to present our work entitled Integrate Photonic Platform with High-Speed Single-Photon Path Entanglement. So as an essential building block for quantum information applications, entanglement can be achieved in discrete variable form from spontaneous parametric down conversion or from spontaneous four-way mixing process, or in the continuous variable form generated by nonlinear squeezing. However, there are still some limitations when preparing entangled states on chip. The nonlinearity for common photonic platform is not high enough. So as an example, the silicon or silicon nitride platform is the most common one, but they lack of second-order nonlinearity. For lithium niobate or aluminum nitride, such kind of material, the fabrication is much harder and it's typically not available in large foundries. And the repetition rate is another issue for chip, which is typically limited by the dead time of single photon detector and the limited bandwidth of homodyne detectors. So for the key contributions of our work, in our scheme, we demonstrated near ideal entanglement on chip using only the noisy PDK components that are not designed for quantum but for classical communication applications. And single photon source and low temperature detector is not required. Here we combine the discrete variable with continuous variable here. The source is a discrete variable source, which is based on decoy states that post-select the single photon contributions, while the detector is based on homodyne detection. We designed the repetition rate up to 10 GHz, and we also proved that in our case, considering post-selection, the fair sampling assumption still holds. The working principle for our scheme is shown in the middle section. The encoder and receiver are all integrated on a single silicon photonic chip. The laser and amplifier is currently off chip, but there are already commercialized solutions to put them together on the same chip. An intensity modulator and attenuator is used to generate the required 3 decoy states intensities, and the modulation speed here is set as 1 gigasample per second. The beam splitter splits the input decoy states to generate the single photon entangled states as shown in the graph. The receiver sharp noise limited homodyne detector here. The output signal are subtracted directly on chip and then amplified using off-chip RF amplifiers. The output results are collected using oscilloscopes. In our scheme, we treat each time sample from the oscilloscope as one quantum state. Thus, a high-speed detector may push the repetition rate higher. As the key components, the result for homodyne detector is shown on the right-hand side. The spectrum shows that the detector can operate sharp noise limited up to around 10 GHz, and the clearance at low frequency is up to 15 dB. So to characterize the prepared states, we first perform a state tomography. By scanning the phase difference between the receiver Alice and receiver Bob, the output from both the homodyne detectors are collected at the same time to analyze the correlation. The resulting quadrature distribution shown in the middle, and it clearly shows the correlation behavior. And using a maximum likelihood solver, the density matrix is obtained and shown on the right-hand side figure. The 0, 1, and 1, 0 components, as you can see, is dominant, and the purity is calculated to be 0.88. A Bell inequality test is then performed. The measurement bases on Alice and Bob's side are switched using a phase shifter. By applying threshold T to the measurement result, we assign +1 or -1 to the result. And the middle figure here shows the resulting correlation as a function of phase difference, and quantum interference is clearly presented. The blue shade in the figure is the simulated upper and lower bound using decoy state methods. The solid line is the simulated result using ideal single photon source. And the testing result estimated value and its upper and lower bounds are shown as dots and the error bar. The CHSH violation result on the right-hand side clearly prove the non-locality behavior, As you can see, higher threshold leads to a higher violation. We can see the CHSH violation at starting from around 0.15, and then the lower bound of CHSH reaches maximum of around 2.59 at t equals to 1.03. So that's our result. As a conclusion, we provide a compact and low-cost platform for quantum optics, and high-speed entanglement can be generated and detected on the same silicon photonic chip. The result can pave the way for future large-scale quantum information applications. Thank you all for joining my talk.